Now, if you take the case of the phasor diagram of the transformer, let us suppose that we have the star delta transformer. Now, in case of what we do, before going to this, what we do, first we have the windings. So we have the two windings. Let us suppose we assume that it's a winding 1:1. The ratio is 1:1. So if you take the we forget that it is in a star or it is in delta. Let us suppose that these are actually the line currents, and these are actually the line currents. In that very case, what is there? If we draw the phasor diagram of that, then in that very case, the phasor diagram would be somewhat like that. That is IA. We will have IA. Then for this IB, we will have here IB. Then for IC, we have IC. So since because of the fact that we are considering 1:1 ratio, and also these are actually the line current, we are considering the line currents. Forget that it is in star or delta. So in that very case, it would be very easy to connect that CTs through that. There is no issue in that. However, problem lies is, let us suppose that we are connecting in star and we are connecting in delta. Now, what happens? So, in case of a star connection, the line current equals to the phase current, like this. IA line current equals to phase current, IB line current equal to phase current, IC line current equal to phase current. Now, in case of the delta, since the delta connection is the starting of the one is connected to the ending of the another, it means that this IA, it is connected to the starting of this IC. So in that very case, the current that is flowing through is IC. So IA, this current is IA, this is IC, the total current which is flowing through it, IA minus IC. Similarly, the current flowing through it, IB minus IA, and current flowing through it is IC minus IB. Now we will we will draw it in this phasor diagram. In a phasor diagram, you will see that it was the previous one. That is, we have the IA, then IB, and IC. Now we have to see the line current. We have to draw the phasor diagram between the line current on the star side and line current on the delta side. So this is IA minus IC. So this is IA and IC is this one. So we add it, then we have IA minus IC here, and this angle is 30°. So from this we conclude that there is a phase shift of 30° between the line current on the two sides of the star delta transformer. Is it okay? Are you able to get it? Is it okay? Are you able to understand that?
Yes, sir.
Okay. Now, equivalent, if you take the case of the equivalent circuit of the transformer, one or more observation that we can see in case of a transformer, and this is actually the magnetizing branch of the transformer that you already know, and this is the series impedance of the transformer. Since the series impedance is very small as compared to that of the yes, shunt impedance, so it is the, because as you know, the current has a tendency to move to the low resistance side. So we can say that it is the series impedance which decides the short circuit current. And if you see, if the series impedance is 0.0 and voltage is 1 per unit, in that very case, fault in the secondary terminal is 20 and 12.5 per unit. So it's very high. Now, what is the most common fault that we have already discussed? The winding to core faults because of the weakening of insulation. Then we have the rare faults or phase faults inside the transformer, and these faults may take place outside the transformers also. However, the variation of the fault current with respect to the fault location within the transformer, it depends upon the what type of transformer connection that we have used, the method of grounding of transformer, and whether the current is being referred to the primary or the secondary side of the transformer. Now we can see one observation. Now what we do, we take the delta star transformer. Let us suppose that we have a delta star transformer and star is resistance grounded in that, and a graph is plotted between the fault current in per unit and the distance from the neutral. Let it be x, so distance from the neutral, and let us suppose that short circuit occur across the winding. So in that very case, that is winding to earth fault occurs in that very case. Now what happens, the when we plot the graph between the fault current and distance from the distance of x from the neutral, we will see that as the distance of x from the neutral goes on increasing, the fault current also goes on increasing on the star side, and on delta side it is also going to increase, because when the short circuit fault occurs, then in that very case the effective between line to ground is, then effective ratio of the transformation is also affected because of that. Now in this is in case of when we have the particular value of the resistance, let it be 1 per unit. Now in another case, what is their resistance? We have taken the resistance 0, so no such kind of this pattern has been observed, and it is seen that on the delta side, though the current is increasing, however on the star side the current is decreasing. Now in another case, what we have done, we have taken this we have used one earthing transformer in that very case. Instead of the resistance, we have used the earthing transformer in that very case, and one observation has been made. And when the plot this is a graph is plotted between the fault current in per unit and distance of x from the end of the winding. From this, we will see that at the 50% of at the center of the winding, when the fault occurs at the center of the winding, in that very case, you can say the fault current is minimum. So these are some of the observations which are made by the different researchers. Now, the faults actually the
Excuse me, sir.
transformer. Yes, batao.
Sir, can you please explain the previous slide?
This one, na?
No, no,
If
sir.
you see
The one
from this,
before it, sir.
this one, na?
The one before it, sir.
This one.
Yes, sir.
Yeah. So I was saying that in this case, you will see that as the what we have done, as we are increasing the value of this, as we are taking this x at this, as we are increasing the value of the x, it means that distance of this from the neutral, as this value x increases, the fault current in per unit also increases on the star side and on the delta side if there is particular value of the resistance, that is Re. However, there is no particular value of the resistance. We have take the resistance as 0, then no such pattern has been observed in that very case. Is it okay?
So when the distance x increases from the neutral point, so
Uh,
why does the current increase? Is it that the
when
effective turns ratio it increases or it decreases?
when it effective turns ratio will decrease, turns
Okay.
ratio effective turns ratio will decrease when x is increasing, effective turns ratio will decrease, and effective turns ratio will decrease, then the current is increasing. Is it okay?
Sir, N1 by N2 in transformer, N1 by N2 is equal to I2 by I1.
I2 by
So that,
I1, so it is actually the inverse of that,
yes,
inverse of
sir.
the
So,
voltage, na?
so when the effective ratio is decreasing, so I2 should also decrease.
No, if you see N2 by N1 equals to I1 by I2, then what is I2 in that very case? N2 by, this is I1 divided by N2 by N1. Is it okay? Then you can say that I1 into N1 by N2. So if effective ratio is decreasing, then I2 current is increasing. Is it okay?
Sir?
Hello? Yes, hello?
Yes, sir.
Is it okay now?
Yes, sir. I understand.
N2 is decreasing. Na? Here, if you take the case of this, N2 is decreasing, then in that very case, what happens? It is increasing. When N2 is decreasing, then I2 is increasing. Is it okay?
So actually, for example, a fault comes at 50% of the winding.
Uh-huh.
Okay, so at 60% of the winding.
Mm-hmm.
The 60% of the winding is getting shorted.
Yeah, it is getting
So,
shorted.
so the 60% that we are neglecting, and only the 40% is now the effective ratio.
Yeah, 40% is effective ratio.
Okay, sir, I understand. I was actually confusing it, sir.
Okay, okay, okay.
Oh,
So now powered and distribution transformers are provided with the on-load tap changer gears. So that is a second issues related to that, then why the fault occurs. So this shows the physical how it is actually physically shown on-load tap changer, which are used for changing the tappings of this and transformer. So if you take the case of OLTC, then in case of OLTC, it looks somewhat like that. And if you see, we can what we have to do, we have to change the tapings so that the voltage regulation can be done according to that. Generally, is this on-load tap changers are generally used for the voltage regulation purposes. So what we do, when let us suppose that voltage changes on the secondary side, what we have to do, we have to change the this tappings on the primary side by using the old load tap changer gears, and because of that the many fault occurs. Like if you see in this case, if you take this case a small example, in that very case, let us suppose the current is flowing in this this bulb, and because of the drop is there in the particular line, whatever voltage is required, whatever is here is not here because drop occurs. So what we do, we will change the tappings on this primary side so that the number of voltage per turn can be increased on the secondary side. So as we are putting more load on this, then in that very the current will increase and the voltage will decrease, and again we can change the tapping. So this way OLTC will work. Like if you see, if you have read also in your machine part that how the OLTC works, it has two switches, that is two selector switches, then the reactor coil is there, then vacuum switch is there, then we are moving this from 1 2 3 or 4 by a mechanism so that we can change that. So it is also one of the reason for the type of faults in the transformer, because OLTC has and the second largest probability of getting the fault. Now types of the faults in the transformer: low level of the oil in the transformer. All the transformers actually are oil immersed maximum, so there is a possibility of the low level of the oil in the transformer. Then we will have the inrush current. Another transformer issue with the transformer is that it experiences a large value of the inrush during the switching, that we can discuss also. It is not a fault but a normal condition, and we can also develop the relay based on that. Then we have the interturn fault. The transformer may develop the interturn fault, giving rise to hot spots within the winding. So it's very difficult to detect that interturn fault by non-electrical means. So we have to detect it by electrical means. We have to detect it by the non-electrical means. Another is the overfluxing. For overfluxing we are using the voltage by hertz relay. So overfluxing will have disastrous consequences for the whole of the transformer. Now we start with the overcurrent protection. So we have already discussed the overcurrent protection. In case of the overcurrent protection, what we do, we use the overcurrent relay. We use the overcurrent relay at the two phases and one ground fault overcurrent relay. So this relay is used as a for small transformer, and for the large transformer it is used as a backup relay. So this is about the overcurrent relay. Now second is the percentage differential protection of the transformer. Now in the percentage differential protection of the transformer, as I already told you, the current is moving like that. First we have to generate the connections, and after that we can see how the current is moving. Now here the current is moving like that. Now these are actually the CTs. So first we must know the direction of the current. So from here, as per the dot convention, the current is moving here towards the dot, and it is moving away from the dot. And again, in case of the CT, the current is moving this towards the dot, and it should move away from the dot like that. So then we develop the connections. Now we got the values of this IA, IB, and IC. Now, as you know, we have to calculate the line values. First of all, we calculate what are the phase currents that is, these are IA and IA are the phase currents. Then we calculate the line currents, because the CTs are always installed on the line. So we have to calculate the line current. So you can say that IA is here and then IC is here. The current that is moving through it is IA minus IC. So similarly, we have to calculate the value of the currents, line current in all the cases. And one more observation is there, that since there is a, as we have already observed, that there is it is the delta, it is the star, the so CT that we have to use in this star delta transformer is delta star transformer is star delta. So because of after using this star delta CT, the all the things that is you can say that the phase difference will be neutralized in that. So that thing we have to take into consideration, because there is the phase difference between the line current in both the cases is 30 degree. So then we have calculated the line currents. Now the line currents are calculated and CTs are installed at the lines of the transformer. Now CTs are installed at the lines of transformer. Now what we have installed the CTs, and after that, as we know that this is a delta, so we have to connect the CT here in the star. So star, what is star? All the points are connected together. That is, here we have this one, here we have this one, and here we have this one. So these are actually connected in the star. CTs are connected in the star, and current that is flowing is IA minus IC. So if here is IA minus IC, so this one, then IB minus IA and IC minus IB. Now here we have to calculate the here this is another side. Here we have to connect it in delta. Delta means the starting of one is connected in the ending of another. So we have the starting of the one is connected to the ending of another. So IA is coming from here. Now if you see, this is IA and this is IB. So the total current, the current that is moving through it is IB minus IA, like that. So IB minus IA. So here, from here also we got the current IB minus IA. Similarly, at this point, if you see, this is IB and IC. So IC minus IB. So the current that is IC minus IB. And similarly, we have the current IA. So, and this is IC. So IA minus IC. So we are IA IC. So it means that if we have chosen the CTs as in case of delta star transformer as star delta, and then in that very case, all the imbalances are neutralized, and here we are getting the current, and spill current that we are getting is 0. Is it okay? Are you able to get it? Is it okay? Are you able to understand that?
Yes, sir.
Okay. So this is, now we can do the analysis of that. How we can do the analysis of that? We can take the different values of the current, external and internal faults, and we can see that what is the probability. Now from this, let us suppose that fault occurs, external fault occurs at C. Now, when the external fault occurs and C, all the C currents will get affected because of that on the primary side also. And then you will see that this C currents are affected, then C currents are affected. Then when the C currents are affected, all the currents where IC is coming into picture, it is getting affected. It is getting affected, and as a result, whatever be the increase in because of the external fault, it is neutralized by the increase in the current on the delta side. So as a result, no current is going through the spill path, and it will not trip. It will definitely not trip. So that is for the external fault. Now, if you take the case of the internal fault, in the internal fault, you will see that in the internal fault, let us suppose that fault occurs at C, because previously it was at this point. Now it is moved at this point. Now as the fault occurs, then all the C is affected because of that. However, there is no way increase in increase in IC on this part and the right part and on the star side, and as a result, the current that is increased because of the increase in the current in IC is going as a spill current, and as a result, fault. This relay will trip. So these connections are actually true. So what we have to do, we have to first of all, we have to mark the connections, we have to take the values of the phase currents. Then we have to calculate the value of the line currents. Then we calculate the values of the line currents. Then after calculating the value of the line current, we have to but we have to take into consideration the dot connection. Now after that, we have to put the CT on that, CT on the line, always based in the line current. And one more observation is that if this is if the transformer is a delta star, then you will have star delta CT is used in that. Then you have to do the analysis, external fault and the internal fault. Then you can see that definitely our transformer is working well. So this is about this how you can design, how you can see whether it's working perfectly or not. Now next is the Inrush phenomena. So can anyone can tell me that what is the Inrush phenomena? What do you mean by Inrush? What do you mean by Inrush? Inrush of transformer. Yes, Hilal.
Yes, sir.
What
So
is the Inrush current?
actually, at the time of switching on the transformer, सर अगर हम स्विच ट्रांसफार्मर को उस टाइम पे करेंगे जब हमारी जो वोल्टेज है वो पॉजिटिव की तरफ जा रही है, जीरो से इंक्रीजिंग टुवर्ड्स इट्स पीक. सर उस टाइम पे जो हमारा फ्लक्स है, इट विल स्टार्ट फ्रॉम जीरो, एंड सर द चेंज इन द फ्लक्स it has to be twice 5m.
Okay, good.
So if it is starting from zero, it will go up to twice 5m, and since the power transformers, they operate near the knee point of the saturation curve, सर जो हमारा कोर है वो सैचुरेशन में चला जाएगा और ये बहुत ज्यादा करंट
ठीक है
लाइन से खींच
इससे
लेगा.
पहले जो भी अभी पढ़ाया, किसी को डाउट तो नहीं उसमें? एनी डाउट रिलेटेड टू दैट अभी पढ़ाया जो डिफरेंशियल प्रोटेक्शन में? कोई डाउट तो नहीं किसी को? हेलो. Okay, I will assume that no doubt. Now, inrush current, that is the full load current, and this is the inrush current. Now, I will explain graphically that what is the this inrush current. As you already know that in case of a transformer, the voltage leads the flux by an angle of 90 degree. So, no need to tell you. So now, in this, let us suppose that let us assume that we are the transformer is working in a working condition, and in the working condition, you will see in a transformer this is the voltage waveform, and this is actually the flux waveform. That is, it means that in the time t by 2, the flux is moving from minus phi to plus phi m, minus phi m to plus phi m. So it means that it is under the normal condition. Now let us suppose that we start our transformer, and at that very time there is no residual flux in that. So no residual flux is that, and the starting what is there, they have to cover that, it has to cover that within the time t by 2, it has to cover it has to change from that is it has to the change of the flux should be 5 to m, that is minus 5m to plus 5m. So change of flux is 2 phi m. So it start at 0, and the change of the flux in the time t by 2, it will be 2 phi m at the starting. So since the flux is increased, and as per the BH curve, when the flux is increased, then we have a large, you can say, large inertia of a current is there in that very case, and that current is actually non-linear in nature. Its nature is non-linear. So that is known as the inrush current of the transformer. It is because of the fact that when we have not energized the transformer, because under the normal condition, when the voltage is cover the distance of t by 2, the flux will change by minus phi m to plus phi m. However, it will change, the change is 2 phi m. However, it is negative, it is positive. So the value is not large. However, when we have no residual flux is there in the system, in that very case, in the time t by 2, when we start the transformer, it has to cover the distance in t by 2, it has to change by 2 phi m. With the change in 2 phi m, it will go deep into the this character, otherwise it is working in this knee region of this pH curve. So this will increase. It will if the flux is increased, as a result, the current will also be increased, which is the nature of this current is non-linear in nature, because its operating point also changes. Otherwise, it was working at the knee point of that. So because that phenomena of the transformer is known as inrush. So we cannot say that this inrush is actually the fault in the system. It is basically it is while starting the transformer, we cannot say that it is the we can say that it's abnormal operating condition. We cannot say that it's a fault in the system. So let us suppose the voltage be represented by this, then phi is instantaneous value of the flux. So then we equate these two values, and finally we are getting the final value of the flux, which is coming out by like that. And k value, the value of the k in that very case, it can be obtained by the initial condition, that is t equals to 0, phi equal to phi r residual flux. And if we substitute these values, the finally we are getting the values as we are getting this value. Finally we are getting the value of the k as this. So actually it consists of this phi consists of phi r Vm by n omega cos of theta minus Vm n omega cos of omega t plus theta. So we can replace Vm by n omega by phi m. Now the flux is a function of following three factors, you can say. That is the residual flux, that is instant of switching, that is theta, and the magnetic properties of the core, the amount of magnetizing current required to produce the given amount of the flux. However, let us suppose that what we do, we will have such type of condition. So under such type of condition, what we have to do, we must have something or some device related to that, so that we don't have that issue, so that it will work fine. So we can set. So can anyone can tell me, sir, that what is the way out of that? How we can manage that Inrush phenomena? Can anyone can tell me how we can manage that? What we have to do?
So I think the difference between the inrush current and the normal full load current is that the inrush current, so it is not pure sinusoidal.
Yeah, definitely. So
Yes.
it is
We
not
can
pure
play with the,
sinusoidal. Yeah, it contains harmonics.
yes, so we can play
So
with
what
them
we
and
have to do? We have some kind of device is there, some kind of relay is there, which is actually which restrict that current, restrict the relay to operate whenever this harmonics are there in the system. So for that, what we have to do, we have to use this harmonic restraint percentage differential relay. Now, in case of the harmonic restraint percentage, as we already know that harmonics are there in the system, and this table shows the different type of harmonics available in the inrush current. So what we do, we will take the spill current, we will take the circulating current, we will filter it, we will find out whether the harmonics are there in the system. And if the in the circulating current we will have fundamental plus harmonic, then the restraining torque is produced. And in this in the spill current, if the fundamental is there, then the operating torque is actually produced. Otherwise, if the harmonics are there in the system, then definitely it will give the restraining torque. So this is actually the we are using the harmonic restraint percentage differential relay. Now this is the actual how it can be implemented. Like you can say that 3 and 4 the fundamental plus harmonic, 3 and 4 here, 3 and 4, then it is a restraining coil. And then 0 and 2 in this case is a 0 and 2, 0 and 2, it is a spill current. It will see whether it is fundamental or harmonics are there. So all harmonics in the spill current, so it will give the restraining coil. Then in case of this, we will have 0 1. Then in 0 1, if the fundamental spill current is there, then it will give a signal to the operating coil. So this is about the harmonic restraint percentage differential relay. And whenever the transformer enrich is there, we have to make sure that we have to make a difference between this whatever the nature of the current in that very case. So we can definitely do that. Now next is the earth fault, this protection of the transformer. So it is this earth fault protection, a restricted earth fault protection. It is also known as, you can say that it is This kind of fault is also, you can say, it is a high resistance ground fault. It is also known as the high resistance ground fault. So you can say that if we are using the differential relay, sometimes it might happen that the value of that current is very less because of the high resistance. So it cannot detect that percentage differential relay cannot detect that. So winding to core fault is a such type of fault. That is, winding to core fault is a such type of fault. That is, it is actually the high resistance fault, and uh, it falls in that category. So we must have more sensitive relaying scheme for that very purpose. So for that we are using the earth fault protection scheme. And in this case, what we have to do, we have used the three CTs in that, and connect the CTs in this case. And if there is some imbalance in that, then definitely the overcurrent relay will operate. So, and this is on the delta side, and this is on the star side. In the star side, we can say that we have to take care of the neutral also. So this is the high resistance ground fault protection on the star side. Now, next is the interturn fault in the transformer. Now, interturn fault, if you see, if you take the case of the interturn fault, suppose we want to detect the interturn fault. Let us suppose that we have a system, here input voltage is 400 by root 3. So we have the 400 by root 3, and let us suppose the current that is initially the current was flowing, that let it be I1 equals to, that is V1 I1 equals to V2 I2. So V2 in that very case, let us suppose that it is open circuit, no current is flowing through it. And let us suppose that interturn fault occurs within the system. Within the fault, the current is flowing. And let us suppose, let us take a case in which the current that is voltage across this winding, let it be, you can say, let it be 5 volt. And the current, let us suppose that it is flowing is 5000 ampere. So when we calculate the value of the I1 from that, when we calculate the value of the I1, so I1 is coming out to be 0.11. So you can say that we cannot say that it's a fault. It's a kind of fault because we cannot detect that, because it's a very small amount of current. So we cannot detect that. So interturn fault has very, you can say that these are difficult to detect using the overcurrent or differential relay. And actually they cause a hot spot resulting in the deterioration of the insulation. So what we have to do, this leads to the development of one more relay, which is known as the Buchholz relay. It means that what we have to do, we have to detect that interturn fault by non-electrical means. Now this is the Buchholz relay. So Buchholz relay is actually, it is used for the protection of incipient faults. What are the incipient faults? Incipient faults are actually incipient faults. So these are actually the faults which are not significant in the beginning, but slowly develops into a you can say very serious faults, and interturn fault is one of them. Now this figure shows the Buchholz relay. The Buchholz relay is installed between the transformer and, you can say, the conservator. So this is the Buchholz relay. It has two type of contacts. One is one alarm, and one is known as the trip contacts. So what we do, what is there? Let us suppose the alarm contacts are connected to the float, and let us suppose that if the level of the aisle goes and decreases, then this float will come down, and this an alarm will go to the concerned person, and as a result, then alarm, it is connected to some panel, and it will show that the oil is less in the transformer. And in the another type of contacts, that is the trip contacts, and when the large pressure is created within the transformer because of the some kind of fault within the system, so it will these oil will move through that vein, and as a result it will trip. It will move through these, and as a result it will trip. So this is the Buchholz relay. And one more thing is related to that, that what we do in case of the Buchholz relay, since we have different type of actually components, they have different type of gases that are getting out of that. So we do the analysis of that gases. We will take the sample of that gases. We do the analysis of that gases, and we will see that what is there, what fault is there in the system, and what type of gases are coming out of that. Like if you have a type of gas is this, then arcing between the construction parts, and then these gases then arcing with some deterioration of phenolic insulation. So we can exactly know from that. So this is about the trapped gases. Now next is the phenomena of the overfluxing of the transformer. Now can anyone can tell me that what is the overfluxing of the transformer? What is the overfluxing of the transformer? Yes, कौन बताएगा? What is overfluxing of transformer? Yes, Hilal.
Yes, sir.
What is overfluxing of transformer?
So actually, when in the transformer, the voltage increases and the frequency remains same. So we have one equation for the relationship between the voltage, frequency, and the flux. When our voltage is increasing, flux is remaining constant. So obviously, the flux through the system, it has to increase. Frequency is remaining constant, voltage is increasing, so flux has to increase to sustain this increase in the voltage.
Okay. So as per this equation of this transformer, we have this standard transformer equation. You will see that flux is proportional to the voltage. Let us suppose that if there is over voltage in the system and the frequency remaining constant, the transformer is is subjected to the higher value of the flux to support the higher applied voltage. So if the voltage is high, then the transformer, then we have the higher value of the flux to support the higher applied voltage. So as you already know, the power transformer always operate at the knee of this BH curve. It operates at the knee of the BH curve. So any increase in the applied voltage, it will an increase in the flux drives the transformer deep into saturation, that we have already discussed. So the transformer therefore draws an excessive magnetization current, and this condition is described as the overexcitation of the transformer. It means that excessive current is drawn from the transformer due to the increase in the voltage, and it increases the core losses and giving rise to overheating of the transformer. And this saturation of the core causes the flux to flow sometimes in the adjacent structures and causing high eddy current losses in the adjacent conducting material. So it's not desired in case of transformer, because if such conditions continue to occur for a long amount of time, then in that very case it should be we should have the relay for that very purpose. And overfluxing also occurs whenever there is the decrease in the, you can say, this frequency, that is the under frequency operation is there. Let us suppose the frequency also decreases, then flux has to increase also. So two factors are there in this. One is the frequency and one is the flux, that we have to take into consideration this frequency voltage and the frequency. And that's why we will have the one relay which is known as the voltage by hertz or voltage by frequency relay. So this voltage by frequency ratio must not exceed the permissible limit. Let us suppose that if the transformer is designed for 1.5 per unit of the voltage, at a rated frequency will experience overfluxing whenever the per unit exceeds 1.25 at the rated frequency. So that we have to take into consideration. So this overexcitation, it can be detected by measuring the by this V by F ratio, by using this voltage by hertz or frequency relay. So nowadays we will have the microprocessor based relays, voltage by hertz relay. We set the values based on that, and after that we will definitely it will work accordingly. Now these are actually the application chart for whatever we have discussed, whatever is there in the transformer protection. For the internal fault, we have phase fault, ground fault, interturn fault, tap changer, then leakage of oil from the tank, then system phase faults, system ground faults, overloads, and overfluxing. Then for the phase faults, we are using the percentage differential protection. Then overcurrent backup, overcurrent at distance we can discuss. Then ground fault, we can use the percentage differential relay, and the overcurrent relay. For interturn fault, we are using the Buchholz relay. For the oil leaks, we are using the Buchholz relay. For the overload, we are using the overcurrent relay with thermal image of the protective unit, and for overfluxing, we are using the this voltage by hertz relay. Is it okay?
Yes, sir.
Any questions related to that? Because a small part of a bus bar is there. I will also start that. Is it okay? Are you able to get it?
Yes, sir.
Any doubts in that? Yes, Farishta. Okay, can I start now bus bar, second one? Just Hilal, can I start that?
So actually, we have completed whole transformer protection today. So if you can please give us time, we will revise all the things, and then in the next class we can start.
Actually it's a small part, na. Then after that I can start another, na. It's a small part, no,
Okay.
not much part. It's a very small
Okay.
part, and I think you must be knowing about that. It's a differential protection.
Okay, sir. Okay, please.
Okay, as you already know that what is the bus bar, it is derived. This bus bar is actually it is a omnibus, derived from the Latin word omnibus, which is no, which is means common for all, and you can say that it's the nerve center of the power system where the various circuits are connected, and you can say bus bar is here is bus bar, and here is the incoming lines, and here are the outgoing lines. Now you can say that if the fault is there in the bus bar, though rare cases of faults are there, so it has enormous damage because it's a nerve center of the system. So when the protective relay operate to isolate the bus bar from the system, so there is a large disruption to the loads, and you can say that and the bus bar this fault in the bus bar are also not you can say it is rare because of the fact that these are located at the switchyard substations. So these are well protected from that. However, at some point, at some areas, still there is the possibility of the fault because of the vagaries of the nature. So, however, in case of the bus bar, you can say that the main causes of the fault is because of the aging, because of the corrosion, because of the salty water, and the breakdown of the insulation, and the foreign objects like lizards, snakes, and all that. So, due to the low possibility of busbar fault, for many years it was considered as unnecessary to provide the protection to this type of operator. So however, with time, it was felt that if that the fault occurs at that particular bus bar, then it will have disastrous consequences because the whole of the supply is related to that. So that's why the protection is provided, but very simple protection is provided with the bus bar. So as you already know that we have the it is concentrated in the small area, so only the protection that is provided is the differential protection in that very case. Now if let us suppose that we have the bus bar, we have the bus bar here, these are the incoming lines, these are the outgoing lines, and what we do, let us suppose the current which is coming at as 1000, 2000, and 3000 ampere here. So let us suppose that if we are using the CT here as 1000 is to 1, 2000 is to 1, and 3000 is to 1, then the issue is that when it is converted into 1 ampere, it is converted into 1 ampere, and it is converted into 1 ampere, and as a result we have the spill current of the 1 ampere. So it is the wrong method of connection. So we cannot connect the this CTs, we cannot connect the bus bar like that with these kind of CT ratio. So what is the correct method of connection? The correct method of connection is that what we do, we will see that what is the maximum value of the current in that very case. So we choose the maximum value of the current, and this maximum that we can take as a ratio of that. The maximum current value do we, and the maximum value of the CT, we can take that at 3000 is to 1, 3000 is to 1, the current is coming out to be 1 by 3, 2 by 3, and here we have 1 ampere, and finally we are getting the 0. So this is the correct method of connecting the this you can say that it is in bus bar. So this is how the differential this protection can be provided in the bus bar. That is, we have to choose the maximum value of the current, and we have to connect accordingly. Now, one more analysis that is there in case of the bus bar. If you see the let us suppose that we are doing the analysis for the external and the internal fault. Let us suppose that we have the external fault in the system. Now, this is the CT which is taking the maximum amount of the current. Now, because of the imperfections of the CT, sometimes what happens, and because of the saturation, the current would not increase. There is no increase in the current. So because of the saturation, the increase in the current would not be as whatever is desired, and as a result, there is the spill current. So that is the malapration of actually this kind of relay sometimes. And if we have done the analysis for the external internal fault, in case of internal fault, you can say that since there is the difference in the currents on the two sides, then definitely the current will flow through the spill path. So for the internal fault, it's okay, but however, for the through fault, for the external fault, sometimes this kind of relay will maloperate. So if you see from this equivalent circuit point of view, if you see that you have the magnetizing branch here, we have the series branch and the parallel branch. And as I have already told you, as the secondary current in the previous some of the previous lectures also, as the secondary current goes on, our primary current goes on increasing, this voltage goes on increasing, and this voltage goes on increasing, the imperfections are getting magnified. So as the value of the current goes on increasing, the imperfections are getting magnified. So if we want to draw the circuit model of that saturated CD, then you can simply represent it like that for any analysis purposes. Now, what is the way out of that? How we can protect that? We can protect that by using a small stabilizing resistance. The stabilizing resistance, the main idea of this stabilizing resistance is that it will not allow this current. It will not allow this spill current. If some imperfections are there in the CT, then it will prevent this relay from operating. So this is that is known as high impedance busbar protection that we are using for the this in case of the bus bars. Now, one more kind of the relay and that is used in the bus bar is the supervisory relay. So what is the supervisory relay? Let us suppose that it circuit breaks. In that very case, what happens that we are not getting the information, and as a result the spill current is there and our relay will operate. That is not desired. So what happens with what the supervisory relay will do, whenever let us suppose that whenever the fault is there, whenever our connections that are connected to the CT, it get broken out. So because of that, the spill current is there, but it's a very sensitive relay before, and its time is less than this overcurrent relay. And in that particular time, the current is flowing and the voltage is across this relay. It is actually the over voltage relay, and as a result, it will suddenly trip because of that voltage, because the time of this relay and this supervisory relay is less than this particular the relay. So as soon as the spill current is there for a very small amount of time, it will operate that particular relay, and as a result, the whole of the circuit will be out. So this is the supervisory relay. So this is the circuit of the how we can protect the three-phase bus bar similarly as we have discussed for the single phase. So this is about the today's this bus bar protection. So tell me any questions related to that.